All set.
Okay, thank you. So it's my great pleasure to introduce today's speaker, Professor Martin Blunt from Department of Earth Sciences and Engineering at Imperial College London. Martin gained his master and PhD degrees in theoretical physics from Cambridge University in 1988. It then joined BP as a research reservoir engineer before moving to the US to become assistant professor of petroleum engineering at Stanford University. In 1999, he moved back to the UK as head of the petroleum engineering and rock mechanics groups at Imperial, and later as department head. So Professor Blunt's research interests are in multiphase flow in porous media, with many applications, including oil and gas recovery, geological carbon storage, and contaminant transport and cleanup in polluted aquifers. So I won't go through the long list of awards he received. I'll just mention that since 2019, Professor Blunt is a fellow of the Royal Academy of Engineering. Today's talk is really a tale about flows in porous media, and I even think we'll have some explanation on how surgical masks work. So as usual, feel free to ask questions during and after the presentation, and after the talk, Prof. Blunt will hang out a bit in the Zoom room for more informal discussions. So yeah, Martin, the floor is yours.
Okay, thank you, Adrien. That was a very nice introduction. I'm absolutely delighted to give this seminar. Actually, one advantage of this remote world is I don't have to travel, although it would be nice, obviously, to meet many of you face to face. So first of all, I'd like to acknowledge my research group. I do have a particularly talented group of students and postdocs at the moment, and actually they've been working extremely well in lockdown because they've had nothing much to do but analyze the data and think carefully about what's going on. But I'll be quite brief. For those of you with different backgrounds, what I hopefully by the end you get some idea that actually flow in porous media isn't some loose subject. It's actually a rather serious scientific discipline in its own right, and it does rather matter. So let's go straight to the chase. What do we do at Imperial specifically? So if you look here, that looks like a medical X-ray scanner that you might see in a hospital. So we use X-rays to look inside mainly rocks, right, not people. That's fair enough, but the main physics occurs at the pore scale, at the micron level, at the interstices between the grains. So we need higher resolution. Now, X-rays can give you higher resolution, you just need a smaller sample. So I can have a sample of about this size. I normally want something a little bit smaller than that. So that's what's shown here. This is about 5 or 6 millimeters in diameter. And then I can get an X-ray source close to the sample, and I can get down to micron resolution, and I can take three-dimensional pictures of this. You notice this sort of gold-colored jacket. What that enables us to do is to impose conditions of high pressure and temperature, like you might encounter deep in the subsurface in the lab. So we can see the rock inside the rock, and we can see the fluids inside the rock at representative reservoir temperatures and pressures. So that's fundamentally sort of what we do. The other thing we can do is, that's great, we can see the images, but each image takes sort of an hour or two to acquire. And we're looking at fluid flow, we're looking at how things move, so we need something faster than that. So we have essentially, X-ray spectacles. If we have a synchrotron source here that's so bright it's ionizing the air that it's going through. Don't worry, the students operating the machine are behind lead-lined glass. But we can then take images of what's happening in the rock at 1 second time resolution. So we can actually sort of have a reading of what's going on. So why is it important? It is true that most of my work and most of the funding is related to oil and gas production. But in fact, in this talk, I'm going to sort of emphasize other applications, because flow porous media is not about the application, it's about the science. But let's look at the applications. So the first is CO2 storage underground. The reality is the world will continue to burn fossil fuels, both as a swing producer and also in heavy industry. I think the oil industry in particular, to have a license to operate, has to be able to put as much carbon under the ground as is released when their products are burned. Otherwise, I think the Western oil industry is about to close down. But that doesn't solve the problem because people will still be producing burning fossil fuels around the world. But if we look at, it's fairly respectable analyses of what is necessary to avoid dangerous climate change and in a way that's economically feasible, we are looking at tens of gigatons of CO2 put in the subsurface each year. That is, in terms of volume, an industry that's as big as the current oil and gas industry. So this is a huge challenge, a huge scientific challenge, because we can't just stuff the CO2 underground. People might reasonably expect us to understand what's going on, right, and understand properly what's going on. But there are other applications. These may be a little bit new to people, but if we're moving towards a low zero carbon economy, one key component there is a fuel cell, which uses hydrogen and oxygen as a fuel to generate electricity. So the hydrogen and oxygen react and produce water. Now you go through the design. For this to happen, you have to have a porous layer, essentially what's called a gas diffusion layer, which is fibrous material. And you want, in the fibers, you want the hydrogen and oxygen to be able to get to the catalyst where it reacts. And of course, when hydrogen and oxygen react, you form water, and you don't want the water to clog the pore space. You want the water to be able to go back out, right? So you want the gas in and the water out. You want them both to flow, right, over a wide saturation range. You don't want anything trapped. Okay. Now let's look at some other applications. And yeah, I've got the famous surgical mask there. So there are lots of other applications where you have fluids in the pore space and you either want those fluids to move or you want to trap them, okay? When it's CO2 injection, you actually want the CO2 to stay underground, obviously. If you want to produce oil and gas, you want the oil and gas to move. The surgical mask problem, the surgical masks are fibrous layers, and I'll talk why there are layers. Obviously, what you want in a surgical mask is you don't want any droplets from someone to go to you or from you out, okay? So you actually want to trap, right, the water, because it's in these droplets that the bacteria and virus are found, okay? And you can have microscopic, micron scale droplets, okay? So, in essence, right, multi-phase flow and porous media can be boiled down, I mean, I'm simplifying, but this is going to be the theme, right, to one of two things. You either want something to be trapped in the pore space. You've got a complex pore space, it can be a fibrous membrane, it can be a rock, it can be a soil, and you want something to stay in it. Okay? And what that means is you want something to sort of be blob-like, right? Sort of almost a spherical blob trapped in some of the larger pore spaces, surrounded by another phase, right? It could be air or it could be water, that stops it flowing. So that's what you want with CO2 storage. You want the CO2 to be trapped in the wide pore spaces surrounded by water. In a surgical mask, you sort of, it sounds like the opposite, but you want any droplets to be captured by the mask and stay in the mask, in this case surrounded by air. Okay, so that's one thing. The second thing you might want is the opposite, really, flow. You don't want the stuff trapped, you want the stuff to move, okay? So you want the phases, the fluids that are in the pore space to flow over a wide saturation range. And the examples there are fuel cells, right? You've got hydrogen, oxygen going in, the water coming out, you want them both to flow. You don't want one of them to sort of get clogged in the pore space, okay? And oil recovery is the same, right? I want the oil to come out. And I normally do this by injecting water. So I want the water to be able to flow, but I want the oil to be able to flow too. Okay? So what controls that? Well, clearly the pore structure does. And actually, that's not going to be the emphasis of this talk. In fact, we're getting a lot better at knowing the pore structure, because you might say, well, use this three-dimensional X-ray imaging. I know exactly what the pore structure is, and maybe if it's a manufactured material, I can design it. Absolutely right. But the focus of this work, right, the sort of thing our group has been doing over the last few years, is look at wettability. Wettability is the local distribution of contact angle. So let's whiz straight in with a video of what I mean. So here is an experiment we've done. This is on a rock, a small rock sample, okay? And what you're seeing there in red are the grains, essentially calcite grains in this case, okay? And what we have is we have carbon dioxide trapped in the pore space. And what you're seeing now in white is that carbon dioxide. And we're looking at a scale here about 1 millimeter across. So these are sub-millimeter blobs of carbon dioxide. The different colors just show the different blobs. Okay, they're surrounded by water, they're not moving. So look at this blob, it is sort of ball-shaped. That's going to become significant in a moment. Okay. And then what we're showing is the image here. We can use different colors. This is an experiment, it's just fancy image processing. Okay, so there's the CO2 there, there's the brine there, the water, and the rock is shown in red. Now the ball's shown in red. Okay, we're just flipping around. But we want to know about wettability, because it turns out that controls everything. So what's shown in yellow is the three-phase contact line where the two fluids hit the solid. And what you have to do is take a plane that's perpendicular to that three-phase contact line. Okay, we're zooming around the pore space and doing that. Okay, and then the contact angle is measured where this is CO2, this is brine, this is the solid. Now, the way it looks like this is the CO2 doesn't like the solid, it's sort of bulging away. Traditionally, actually, of course, we measure contact angle through the water or the denser phase. So the contact angle normally, traditionally, will be measured here, and it's about 45 degrees. So this is water wet. Water likes the surface. So the water likes the surface, the CO2 doesn't. It tries to stay away and can get itself trapped in the larger pores. So that's the idea. But let's look at the dynamics. Let's look at this X-ray spectacles, so to speak. Okay, now I'll go back to having a highlighter now. Okay, so what we're seeing here is we're having water moving upwards, okay, through the pore space. I'm not showing the rock and I'm not showing the water. I'm showing, in this case, the oil shown in yellow. Okay, so the water's moving up, and what we're seeing is the water sort of creeps along, fills some of the narrow regions of the pore space because it likes the surface, okay, and surrounds the oil in this specific example with water. So let's look at that, one might say, in a little bit more detail. Okay, so we can zoom into this image. Okay, so here we have it. Now the oil is shown in red. Okay, so what happens is the water displaces the oil here, it pushes it out. This narrow region of the pore space, the water, again, you can't see the water because just to make it clearer, the water pinches off or snaps off is the technical expression here and forms this ball-shaped blob of oil in the pore space. Okay, this image here is just fancy stuff, right? It's just rotating around so we can see it in different directions. So this is what we've imaged. This is an experiment at a synchrotron where we've looked inside the rock and we've actually imaged the displacement process. And we've seen the trapping. So here are some other experiments. This is where we inject CO2, right? So this is a small piece of rock. The blue shows the CO2 that's connected in the pore space. The other colors show the bits that are trapped. You inject the CO2, it can move. So this is a concern. You inject the CO2 into the subsurface, it's going to move. But when it moves, it leaves behind a trail of trapped CO2. So after water has moved in to displace it from the pore space, you get about a third of the pore space filled with trapped CO2. And again, the different colors are different blobs. And you can actually measure this. This is how much CO2 we put in. This is how much gets trapped. And in this case, this is CO2 trapping. In this case, we put about 50%. We trapped about 30%. So about 2/3. What we put in doesn't move, and then it moves to the next region, and then 2/3 of that gets trapped. So actually, the CO2 doesn't migrate that far. It gets trapped as these pore space bubbles, essentially. So this is pretty heartening. For those of you petroleum engineers, it's not such a surprise because we know oil can get trapped in an oil reservoir, and regardless of what we try and do, we leave half the oil behind. So the fact that the CO2 can get trapped in the subsurface maybe is not a revelation, but we can see it clearly. But now I want to do a little bit of an aside, because, okay, that's fine, and I could sort of worthily plod through other work we've done. But I want to put this in a more, one would say, mathematical or physical framework. So first of all, this is just a a sort of teaching slide. Okay, so we're interested in interfaces between two fluids. In the end, we got two fluids in the pore space, and there's an interface between them. And this interface is characterized by curvature. Curvature is quite easy. If we've got a line at any point, it's the circle that fits on that line, and the circle has a radius, and the curvature is the inverse of the radius. Okay. Of course, we have 3 dimensions. Okay. So we have 2 what are called principal radii of curvature in orthogonal directions, and we have 2 curvatures. Right? And these curvatures, if we think about a ball, right, the 2 curvatures are the same, they're just the radius of the sphere. But if we have something, say, like a pear, we can have something that sort of, the pear bulges out in one direction, but in the other direction, the whole idea of being pear-shaped is, of course, it has a curvature that bulges in. So it actually has a different sign. Okay, so the curvatures can be distinct. And then we immediately have a couple of things. One is a capillary pressure. There's a pressure difference between the phases that's proportional to the total curvature, the sum of the 2 curvatures, times the interfacial tension. So that's useful anyway, just as a characterization. The 2 phases have different pressures, okay, from the Young-Laplace equation. Then we can define something else called the Gaussian curvature, which is the product of the 2 curvatures. Okay, well, we can do anything, 2 numbers, so what? Okay. But now we get to something rather intriguing. It's the Gauss-Bonnet theorem. It's something that's well known, but its implications for flow in porous media are just being explored. If I take an object, I've got a piece of plasticine in my hand. If I integrate the Gaussian curvature, this product of curvatures, around the surface, it doesn't matter what I do with it, with my hand, as long as I don't create any holes or loops. The integral is 4 pi times what's called the Euler characteristic. And for a blob like this, it's 1. Okay. So what's the Euler characteristic measure? It's basically the number of objects you have. So imagine, it's CO2 and you want to trap it in the pore space. So it's the number of blobs of CO2 minus the number of loops. So the CO2 can form loops in the pore space. But of course, that keeps it connected because the water might snap off, break the CO2, but it's got another escape path. All right, so the loops are bad, plus the number of holes. The holes are less relevant. What they would reflect is the CO2 completely surrounds some water, and you never actually really see that. Okay, so here's some examples, right? Also shown in yellow, like my plasticine. So a sphere, but anything that's manipulated from a sphere, right, is has this Euler characteristic 1, and the Gaussian curvature integrated over the surface is 4 pi. Okay. So Gauss, called it a remarkable theorem. It is quite remarkable. And then if you have 2 objects, it's 2. If you put a hole in one object, then it's 0. You put 2 holes, it gets -1. This cage structure, you actually have to make it to discover that it has 5 loops. Okay. Fine, you might say. So what is it? So if you want to trap something in the pore space, right, if that's your idea, right, CO2 storage, surgical masks, then you want one phase, the phase that isn't trapped, right, to be wetting, right, which means contact angle is less than 90 degrees, so that the other phase, the non-wetting phase, is trapped. And this is well known, okay, so what? But in terms of curvature, what this means is that you have these sort of ball-shaped interfaces. I mean, and we've measured it now. You have, in the pore space, approximately equal radii of curvature. So the Gaussian curvature is positive, right? So that means that the Euler characteristic is positive, and that means there's lots of trapping. Lots of, things curl up, they get trapped, they don't flow. Okay, fine. That's a sort of mathematical way of saying something new. Okay, why did you want things to flow? Now, it's on the slide, it might sound a bit obvious. It hasn't been obvious in the oil industry because people have said, okay, we want the oil to flow. What's the ideal condition? What people normally say, well, just a moment, water wet things get trapped. So maybe we want the oil to be the wetting phase. That doesn't work. I mean, it's obvious, right? Because if oil is the wetting phase, the oil lights the surface, it sort of gets retained, sort of soaks into the rock, and you can't get it out. So actually, we know that oil wet isn't good. So you say, oh, okay, maybe it's contact angle. Maybe, contact angle of near zero isn't good for trapping, and 180 isn't good because then it soaks up the oil. So maybe a contact angle in between. And that's sort of right. And it hasn't really pinned it down. What's the opposite? The opposite is where the radii of curvature are equal and opposite, so different sides. Okay, so one curvature is minus the other, right? And it's the difference between apples and pears, right? An apple, okay, it's supposed to be ball-shaped, right? It's not very ball-shaped, but anyway, it's a ball, as opposed to something that's pear-shaped like this. So surfaces with equal and opposite curvatures are called minimal surfaces. They are a hot topic and have been a hot topic ever since the days of Euler. So minimal surfaces have a negative Gaussian curvature, but the mean or the total curvature is zero. And here are some examples. This is a helicoid, like this. A more familiar is a catenoid. It's actually, you know, if you have a string and you rotate it, you form a catenoid. It's exactly the shape you get with a soap bubble. Okay. And the reason is, it's obvious. You've got a soap bubble like this, okay? It has to have a curvature around like this where it attaches to the ring. So it has to have an equal and opposite curvature the other way, because what's the difference in pressure between here and here? Zero. So the capillary pressure, the pressure difference across the interface has to be zero. The only way of doing that is if the curvature, the total curvature is zero. Okay. But it also means that if you have two phases on either side, they tend to be well connected. So this looks like what's ideal for flow, but so when do you see them? Well, mathematically you can prove that when you minimize surface energy, where the three-phase contact line is pinned, it's held in place. So a bit like this soap bubble, right? The soap, the film has to, well, it's not a bubble, it's a film, isn't it? Right, the soap film has to be on the rings, okay, so they're held in place, and then any interface there is a minimal surface. Okay, and we see them in lots of different cases, and we can engineer this in porous materials. So for instance, if you look at bones or artificial bones, okay, you want the bone structure to be strong, so you want the solid to be strong, but you want lots of holes for the blood vessels. How do you make it? Minimal surface, okay, because you get best connectivity of both. So how do you get that in a rock? In rock, you actually have what's called, you can often have, typically, what's called the mixed wet state. And the reason is that, imagine this is a bit of the pore space, so here's the solid, we've got some angular bit of the pore space. Oil moves in, it sits there, high temperature and pressure for geological time, oily, basically surface active components of the oil stick to the surface. So you have an oily surface here and a water wet surface here. The oil pushes the water in, right, at a high pressure, it's curved like this. Now I inject water, I want the water to move, there will be some displacement, but not until this contact angle increases till the water is actually bulging out over the oil. So funny enough, if we get a mix of wettability, some oil wet patches, water wet patches mixed together, then many of these three-phase contacts can't move because they sort of got to get over the less favorable wettability next door. So rocks in contact with crude oil, soils with organic material. And if you have an engineered material, right, you want a mix of something that's hydrophilic, likes water, and hydrophobic or oily, doesn't like water. So do you see it? The answer is yes. So we've done these experiments. Here are the oil-water interfaces in the water-wet system when the oil is trapped, lob-shaped. Here is a measurement of the curvature. The curvatures are positive. Then we had a rock that had been in contact with crude oil. We see these interfaces are much more complex. They are not sheets in the sense of being flat, okay? They can't be flat because of the geometry. They have to have a curvature, and then they have another curvature that's in the opposite direction. The mean curvature is almost exactly zero. Okay. And this, as we're going to show later, leads to good recovery. So that, in essence, is sort of what I wanted to say, right? You've got flow in porous media, you want to trap something, you want to have these positive curvatures, strongly wetting conditions, you want something to flow, you actually want a mixture of wetting conditions with this negative Gaussian curvature. So let's having made that framework, we can then, move ahead, right? The first one, I'd have to say, if you're into oil recovery is, okay, prove it, right? Actually measure something, right? Second thing is we can use these ideas actually to look at wettability, because it all hinges on contact angle. So we've got some cool ways of measuring wettability. I've talked about oil, water, and air. What about if you have oil, water, and gas all together? And then I'll show you, back to Marston fuel cells, but you're probably getting the idea how they're going to work now. So let's quickly look at rocks. So here is a reservoir sample from the Middle East, where we've got oil and water. So we start off with mainly oil and a little bit of water in the small pore spaces, right? Red and blue. And then we inject water. This is a fractional flow. It's the volume of water injected divided by the total volume, right? So it's 95% water, right? And you see when we get to 100% water, we've displaced virtually all the oil from the pore space. So we can see immediately, this is looking good, and it is in the mixed wet state. And the reason for it is, here's an image, and again, we're just looking at a couple of millimeters across. We're imaging the water. And what happens is the oil has changed the wettability. It's mainly oil wet. So the water now is mainly a non-wetting phase. It wants to go in the big oil wet pores. So it does that. It can flow in the nooks and crannies of the pore space, and there's what's called microporosity, very small pores that are always full of water. So it moves in these big pores, but the water's not connected. You increase the fractional flow, it's displacing an awful lot of water. The water only gets connected at a very high fractional flow. What that means, in terms of what's called a relative permeability, how well things flow as a function of saturation, the water doesn't really flow very well. The oil doesn't flow that well either. The oil relative permeability goes down because the oil's going into smaller and smaller pores. But there is flow over a wide saturation range. And in fact, in oil recovery, you want the oil to flow more than the water, right? Because you want to be producing oil, not water from your reservoir. And you want to push where these two relative permeabilities, where the flow is similar, basically to higher and higher water saturation. This is great for recovery. So in the Middle East, there are many reservoirs which hit this sweet spot of the mixed wet state, and actually water flooding can be extremely favorable. Not in all cases, right? It's not a universal statement, but in many. Now, let's look at wettability. Can we be a little bit cleverer than this sort of, fancy video and then sort of almost, by hand measuring the contact angle? Well, we can do it automatically now, right? We don't have to zoom around and do it by hand. We have algorithms that can do it. But there's an even cleverer way. Imagine we've got one phase here sitting on a solid surface. Okay, this is the contact angle. Now, we know that if we integrate around the Gaussian curvature, that's 4 pi. But it isn't, is it? It's 4 pi plus, it's 4 pi minus a bit, because here there's a discontinuity in curvature, right? So where there's a three-phase contact line, there's a kink. Now, in 3D, you probably don't see it straight away, but in 2D, you know, right? You know that the external angles of any polyhedron is 2 pi, right? The sum of the external angles. And then if you have a shape that has some curvature, it's the integral of the curvature plus all the angles equals 2 pi. Gauss-Bonnet, okay, it's a little bit more complex. It's the integral of the Gaussian curvature plus these discontinuities, actually turns out to be 4 pi. So what we can do is we can actually relate the contact angle to an integral over curvature. And the reason why this is beautiful is actually measuring the contact angle from an image is really tricky. You've got to have a super high resolution image. You've got to segment it. There are lots of uncertainties. Whereas integrating over a two-dimensional object, which is your interface, is much, much more accurate. So this potentially is a breakthrough in our characterization of wettability using this, Gauss-Bonnet theorem. So it looks great. It's all very recent, all been done this year. I'm not actually going to show many results. We can talk about it later, but it's very promising. The second thing is, we talked about these pinned contacts in mixed wet systems. So actually, the contact angle is a bit of a dummy because it sort of can be anything. So actually models what we want when we want to simulate this behavior. And again, I'm not going to talk about models in this talk. Is actually we want to know the contact angle when something actually moves, when one phase displaces the next. And the way we approach that is actually from an energy balance. Okay, so again, I'm not going to derive it right here, but it's relatively straightforward. You know there's a capillary pressure between the two phases, right? Because there's a curvature of the interface. One phase pushes the other. It's PDV work, classic, first year, physics 101, right? PDV work is converted into changes in surface energy. So we replace phase 2 by phase 1, right? And the difference in those interfacial tensions, which are basically an energy per unit area, is from the Young equation, just a sigma cos theta. So contact angle pops into the equation, and you go through it and you end up with this equation. This is the change in the area between one phase and the solid. Here is your contact angle. Here's your curvature that comes into the capillary pressure. Right? And here's also, we can create more interfaces between the two phases. Okay, so it's relatively straightforward. The beautiful thing is we can measure all of these, and they're just looking at areas and curvature. And it's when there's an actual displacement, so it's in the places that matter. Final bit of theory is talk about oil, water, and gas. And we're going to talk about this, if you're going to make fibers for surgical masks or in fuel cells, what are they made out of? They're made out of plastic. What's plastic made out of? It's made out of oil. So they're obviously naturally oil wet. But actually, we want them to be repellent to water in the presence of air. Now, most people sort of get this, well, that's sort of obvious, right? An oily surface repels water. It's obvious again, anywhere except the oil industry where there seems to be some sort of revelation. So we actually need to go through it a bit more carefully. We've got 3 phases, oil, water, and gas. We can write down Young equations for all 3 of those fluid pairs. And then what we do is we take this equation and minus this one, so we get rid of sigma gas solid, and we end up with this equation, and then add it to this one, and lo and behold, all the solid interfacial tensions disappear, and we get a Bartel-Osterhofer relationship, which is a relationship between interfacial tensions and contact angles. So what does that mean? Well, why ducks, or indeed surgeons, don't get wet is because if we have an oily surface, the oil-water contact angle here is negative. The gas-oil contact angle can be positive, but the interfacial tension is normally less than this. So this means that this right-hand side becomes negative. This means the cosine of the angle between gas and water is negative, which means the gas-water angle is greater than 90, which means water forms a droplet, and in fact, the gas is the wetting phase. So here's an illustration of it. Okay, here's a leaf. Okay, leaves are waxy, obviously because they want to repel water so that when it rains, otherwise the leaf soaks up water. They need to respire and they need to expire oxygen, right? They need CO2 and oxygen to move through the stomata. They soak up the water from their roots, and then water vapor leaves the leaf. You can't soak the leaf. So what we have here is, we put a water droplet on. The water is non-wetting in the presence of air. What I've done here is I've poured some olive oil on the leaf, and the oil is soaked into the leaf. Okay. Right, and it's the same thing, when you have oil slicks. Why do seabirds suffer so much is because their feathers are oil wet to keep them dry in the presence of water. When they hit oil, it soaks the oil, right? So, okay, so last bit of results from ROCS anyway, the sort of culmination. You can see the date of the paper. I've managed to get to 2021 in publications. If we can only get to 2021 in real life without drama, that will be unexpected. Let's put it this way. Okay, so moving it on, we can do the energy balance for 3-phase flow. This is pretty cool in terms of the mathematics. Okay, there's the equation. And we've done some beautiful experiments. My brilliant students have done some beautiful experiments. And so we can actually look at wettability and behavior. So if we have a water wet rock, it's water wet, so oil-water contact angle is less than 90, obviously. And then it's also, the gas is also the most non-wetting phase. So This is actually quite bad for recovery because I inject gas, the gas just channels through the rock and you don't produce much oil. That's well known. However, the oil industry is obsessed with this idea that gas always is the most non-wetting phase. It always flows through the big pores. It always flows readily, so why bother injecting gas? Wrong, obviously. If we have a reservoir sample here with an altered wettability, the oil-water contact angle is greater than 90 degrees. Obviously, it's more oil wet. But as you can see, the contact angle between gas and water is also greater than 90. So in fact, gas does not go in the big pore spaces, water does. So the gas actually is confined to narrow regions of the pore space. The water can get trapped. And actually, this can lead potentially to more efficient displacement. So we're heading here, in the end, towards a sort of basically a complete characterization of porous media flow. And it's not just us, it's a group in Australia, Australian National Lab. The idea is we're taking all these images and we can characterize more or less completely the topology, the shape, the behavior of what we see in the pore space from what are called these Minkowski functionals, which are volume, which is saturation, that's obvious how much we have, areas, and obviously we're looking at the interfacial areas between the fluids, the curvature, which gives us capillary pressure, and the last one is Gaussian curvature that tells us about connectivity. Are we going to flow or are we going to be trapped? We can characterize wettability. In fact, we can relate these Minkowski functionals together to give us a contact angle. We're measuring relative permeability, so we actually measure directly the flow properties. We can do this simply by putting a pressure transducer across our samples. And it gives us a much richer characterization that hopefully will tie into lots of theories. And of course, Paul Rubin hasn't been mentioned here, but you know, there have been a number of people who have working on a much richer characterization of multiphase flow in porous media. And potentially this could help by the measurement of other properties. So let's go back to surgical masks and fuel cells, and then that will be the end of the presentation. Hopefully by this stage you've sort of got it, right? So you've got a surgical mask and you want to repel water. The mask, I mean, if you've, sorry, I normally have a mask to hand. It's in the other room, right? But actually, if you dip a proper, you know, one of the genuine surgical masks, not some sort of handkerchief you put over your mouth, they're water repellent, obviously. So they're made out of plastic fibers, okay? So you might say, well, that's fine. You just have this oily plastic fiber and it repels water. It's more subtle than that. The reason why it's more subtle is that you can also, that's fine if you sneeze and you get these obvious droplets, but you also get this fine aerosol, and that's the most dangerous. And the reason is that this fine aerosol, the droplets are smaller than the pore size, so they can just fly through the pore space. And you might say, oh, you make it a tighter weave, right? You make the pores smaller. Well, then you can't breathe through the mask, okay? So what you have to do is you have to have layers that are hydrophobic to trap the big droplets. But for the little droplets, you actually want them to be hydrophilic. You want them to attract the water. You actually want the water to stick on them. So in fact, in surgical masks and the real respirators that are used in operations, you have layers of water repellent oily fibers, and then you either have a water wet or even what's called an electret membrane that is charged to attract the little droplets. So you actually want both wettabilities alternating. Okay, you normally have 4 layers. So the question is, that's what happens. I can explain it. Obviously, normally these masks have been designed largely empirically. Right? You know, put it together and see if it works. The question is maybe that this characterization approach can allow us actually to design these things more effectively. And the same with fuel cells. So with fuel cells, how do they work? They have these carbon fibers, because the carbon fibers conduct electricity. And again, empirically, what they do is they coat some fraction of them with Teflon, right, which is this non-stick material, right? So it makes it hydrophobic. So in fact, you get these fibers of different wettabilities. It makes a mixed wet state, and that prevents the water essentially being retained in the pore space. And again, that's done empirically. People sort of mix the fibers together and hope for the best, and then concentrate on the electrochemistry, which is obviously fine. But I think porous media has a role here as well. can we actually design these membranes or these gas diffusion layers, as they're called, as effectively as possible. So that's where I'm going to end. Obviously, hopefully plenty of time for questions. Does it matter? I mean, even, clearly, people had their view about, should we even be thinking about enhancing oil recovery? Fair enough. But we need to do something with the CO2, and that needs to go underground. If you think we're going to plant, if the oil industry thinks it's going to get out of trouble by planting trees, well, then maybe they should visit California or Australia or Siberia or the Amazon, or list goes on. Okay, so it's not safe to plant trees. It is safe to put the CO2 underground. And then there are lots of other applications, and I think a growing number, where we can use these insights to design manufactured materials. Right? And I've just given the fuel cells and the surgical masks as examples, because obviously they seem to be a little bit more of interest at the moment. So I will now have my acknowledgements. Okay, unashamedly, yes, actually almost all of this work has been funded by the oil industry. Some of it, actually a significant amount, to look at CO2 storage. And obviously I'm plugging my book. This book was written 3 years ago, and I used to say, ironically, I hoped that very soon it would be out of date, and actually it is. So none of these ideas on curvature and minimal surfaces are in the book. This is all things that have happened or been discovered relatively, or appreciated relatively recently. Anyway, thank you very much. That concludes the talk.
Thank you very much, Martin, for this great talk. Thanks for the explanation about surgical masks. Does anybody, if anybody have a question, feel free to just jump in.
I have a question. Shall I jump in?
Sure.
Yeah, come on, Ruben.
Martin, that was fascinating as always. Your talks are fantastic, and this was no exception. I would like to make a quick comment and then see your reaction to it. So we've done some recent experiments, very simple experiments in a capillary tube. The novelty in those experiments is that we have spontaneous imbibition at a constant rate. And the way in which this is done is by having actually 3 phases. So the air that is being pushed out and the water that is imbibing in, and in between, sandwiched in between, there is a slug of oil. And the oil is much more viscous, and that keeps the viscous resistance is enough and is constant, so as to keep the overall rate constant as well. So the fact that it's spontaneous and the fact that it's constant rate or constant velocity really allows you to isolate the sources of dissipation in that displacement. Okay, so this is the preface to the comment and the question. So one of the things that what we found is that the amount of dissipation that one can ascribe to the moving contact line is very, very much not negligible. So if I go back to one of your slides in which you have a breakdown of the energy dissipation and displacement, I didn't see that.
No, okay, you're absolutely right.
If you have, especially if you have ganglia that are in contact with the rock, that appears to be significant, as in sometimes overwhelming contribution to the energy dissipation.
Okay, that is an excellent comment. In fact, this idea of this energy balance has been, one might say, has received a mixed reception, would be a polite way of putting it. So the answer is, yeah, the big assumption in the energy balance is the viscous dissipation, which is ignored. Okay? So we have looked at that, and we looked at that quite seriously. So we've done, I agree, maybe not, because it is, maybe the reality is a little bit different. So we've done lattice-Boltzmann simulations, and we've quantified the degree of viscous dissipation. We find it's very significant in primary drainage, and I suspect it's also, by analogy, going to be significant in essentially primary imbibition, right? Because you're right, you get a lot of dynamics. We find that in secondary imbibition and in mixed wet media, there isn't a great deal of dissipation in the simulations, and when we apply it, after all, we've applied it to our experimental data sets, I agree they're really complex, but the fact that we get sort of reasonable looking answers gives us an idea that maybe most of the energy is going into the interfaces. And I think the reason is that in secondary imbibition, there's water already present. So the actual movement of the interfaces is relatively small. Right? It's just a little bit when it snaps off. In a mixed wet medium, as I said, most of the interfaces are pinned most of the time. And then most of the displacement occurs at an almost zero capillary pressure. So it's an almost, the PDV work that you put in is almost zero. So there's no real energy to dissipate. It's more rearrangement in the pore space where you're looking at an equilibrium of surface forces. That's my hypothesis. I'm not saying it's necessarily right, but let's put it this way. The unexpected success of the approach gives us the impression that maybe, it's not overwhelming in many of the cases we're looking at. But certainly in drainage, and I would say primary drainage, primary imbibition, absolutely yes. We can't apply, and we know that.
Thank you, Martin.
I have a couple of questions. This is Aimee. Hi, Martin. Very, very interesting talk. So I have an engineering question and a sort of theoretical physics question. The engineering question, maybe I missed it, but in terms of sort of trying to find an optimal solution for, say, CO2 storage, what are the sort of parameters that might be controllable that would optimize the pore situation? Because now I think you've shown that we understand what will cause traps, but now I want to store. What can I do? Is there anything I can do with temperature or pressure or some physical application to control the trap quality of a given reservoir?
I'm going to stop the share. So right, now I can see everyone. Right, great. So what can you do? Yeah, this is one problem. And it's true also, for oil recovery. There's not a great deal you can do in design. It's more characterization. It's more saying, yeah, in this formation, you will trap this, and, therefore the plume will only move.
So you can make choices.
You can make choices. So, I mean, in theory, you can do things. You can change wettability through changing salinity and temperature and pressure. The evidence for CO2, when you change temperature and pressure, is ambiguous at best. Most, in general, if you've got CO2 in a supercritical state in an aquifer, it's non-wetting, and actually the trapping mechanism works well. So there isn't much to design. There was actually quite a lot of debate some years ago, thinking that maybe particularly calcites could become CO2 wet, right? And so then the trapping mechanism wouldn't work, but that hasn't been realized. So
you're saying CO2 works pretty well without engineering?
I wouldn't go that far. I think the trapping, you can assess the trapping mechanism. You also need to assess, obviously, the pressure buildup. But I think in general, yeah, I mean, if I were to ask a more general sort of policy type question, what's stopping us doing large scale CCS is not actually scientific, a lack of scientific understanding, despite how I sort of puffed it up. I think the reality is it's a lack of political will and economic incentive.
Yeah. And then my theoretical physics question is, I think, do I have it right? These studies sort of require, I mean, you have observational studies, and then you have direct numerical simulation of flow in porous media. And then you have maybe some idealized toy model numerical simulations. Yeah. Is anyone developing like a statistical mechanics of flow in porous media? Because I would think the pore geometry doesn't really matter. And it'd be very hard, but maybe some smart person has done something where you just want the macroscopic quantities from some kind of appropriate ensemble averages of the microscopic ones with some assumptions. Is that a program that anybody has? I don't know how to do it exactly. But.
You're absolutely right in what we do. Mainly now what we do is observations, right? We do direct numerical simulation, as you said, and we do this pore network modeling, which I didn't discuss today. What would be great, and what people would like, is if there was some relatively simple characterization of the pore geometry, say, and wettability, from which you could derive macroscopic parameters without, say, direct measurement or simulation. no one has really managed to get there yet. Unfortunately, it seems to be quite when you get, for instance, to relative permeability, the flow properties, it's really quite a subtle balance of wettability and pore structure and how it connects. And so in the end, you sort of have to simulate it or measure it. But, hopefully I'm wrong, but there is a breakthrough there.
Thank you.
Any other question, or someone wants to jump in for a comment?
Adrien, one question.
Sure, Philip, go ahead.
So Philip speaking there. So thank you, Martin and Ruben, because we worked very hard when I was in Total, in the scientific division in Total. So I know this works, but I have a question about the upscaling law from the pore level to the Darcy level, for example. And I read now some paper, and I work also by, as you mentioned, Martin, by energy balance. Could be something we could effectively explain, some mesoscale coming from pore to the macro level. And also I have some friends working on what they call the TK, that means thermodynamics control of range theory, using not the balance of energy, but the entropy as an upscaling law from the pore level to the macro level. What do you think about this kind? Of course, that means a very huge supercomputer for calculating the problem and the data simulation with the real rocks. But the idea using the entropy as a upscaling function and quite solving the equilibrium and the compromise seems to be a good idea. So what do you think about?
Yeah, I mean, the answer is, I think there is opportunity for major breakthroughs in the theory, which I haven't sort of stressed here, and I'll tell you why, is, and it's a bit like the energy balance. The energy balance is a two-liner, and Norm Morrow basically did it 50 years ago. There's nothing clever about the energy balance, and it makes some obvious assumptions, as we've been pointed out. The new thing is you can measure the terms, right? So you can use it, and it seems to work. So one of the problems with all these other theories is they introduced additional characteristics, right? They introduced interfacial areas. They needed to know this, they needed this. We couldn't measure them. So you did a lot of mathematics and you ended up with complex equations with undetermined parameters. The beauty now of this three-dimensional imaging, that's why sort of our group is throwing most of our energy into this, is that it gives you the data that is needed to inform these models. So it then enables us to say, right, well, actually, maybe these models can be used and they can be tested properly. And that's sort of how I'm thinking. We're not ourselves working on these theories, certainly not at the moment, but my hope is that this work helps inform these theories by basically giving the parameters and allowing it to be tested out.
Okay.
Martin, just a quick technical point about your microphone. It tends to drop from time to time, and
Yes,
it doesn't drop to zero, so that's okay. But you might want to do tests.
What I have to do is I have to keep shouting. I know that. I'm getting a new microphone, but that's only next week, I'm afraid.
Right.
And it's even worse if I don't use the microphone at all. So I apologize.
Thank you.
Well, excuse me, Martin, but I do not understand this because a lot of noise on the line. So please, could you repeat the essential of your question, of your answer, please?
So what I was saying is that we're not working on these theories, but potentially we could have a major breakthrough in this area. And the reason is that we can measure many of the properties that are in the theory. So if you do a thermodynamic averaging of the macroscopic equations, you introduce new parameters. So you introduce interfacial area, you introduce curvature, you introduce other saturation, time dependence of saturation. So we can measure these properties now. So we can put them in the models and see if they work.
Right.
Right? Whereas hitherto did this beautiful mathematics, but you couldn't really test it out. That was the problem.
Okay. Yeah, effectively, I agree. Effectively, there's a problem with the capillary pressure, a lot of things, how to measure it, and so, and what is the the curving law of this capillary pressure. So I know it's very difficult. That's the reason why they use a very huge supercomputer. But I think that something could be done by this way, and after perhaps we may have a good advantage. But I agree with you. For the moment, it's assumption.
Thanks, Philippe. Thanks all. It's already 1, so we can say it's maybe officially finished. But I think Martin has a bit of time to hang out in the Zoom room.
Yeah, it'd be my pleasure. My pleasure.
For more informal conversations. So yeah, feel free to stay here and yeah, talk about whatever you have in mind that you didn't dare to ask during the seminar. And yeah, I